All right. So let's start by reviewing a few things from the last class what we learned, and then I'll just give you an intro into uh, what we teach today. Today we'll be talking about convolution neural networks and recurrent neural networks, and from there on, I'll actually cover a little bit of. So let's see if we get time. I'll do TensorFlow, or else we will do variant descent. So did you have any questions from last class? Do you guys have any questions from last class? So any questions from last class?
Not really. The theory part was fine.
Okay.
Yeah.
So we'll look into something. So today we'll cover a little bit more. I'll talk a little bit about the Keras package, which we will do one case study. I did cover it last time, but we'll go into little detail, and then we'll look at two deep learning algorithms. One is called recurrent neural network, and other is called convoluted neural network. We will see why each of them is necessary for us to learn, uh, and we'll. So I won't be going into detail. I don't think we have any exercises on RNN and CNN as such, because they themselves are itself a course on its own, like deep learning, because it's a lot more detailed in like I talked about transfer learning a little bit last time, where you can train another neural network and then transfer some of its learning from the hidden layers to your current neural network. We will see how we can do that using Keras and stuff, but we won't go into like too much detail uh, with with the deep learning networks. But I'll do cover enough so that in case you come across the recurrent neural network or convoluted neural network, you will convolutional neural network, you will actually be familiar with what it is, and we'll take it from there. Just for a quick recap, we did neural networks the last class. So a couple of things why neural networks are used is because they're capable of drawing these non-linear boundaries which can separate classes. If you actually look at the problem, even support vector machines also do that. But if you look at it closely, a support vector machine also does linear boundaries, but on a different dimensional plane. If it is non-linear in this plane, it will project it into another plane and then do a linear classification. The main things which a neural network actually has is something called as input layer. Input layer is the layer where all your features, where x1, x2, x3, x4 are each individual features, and they are connected to this input layer neurons, and then these neurons are connected to another layer. This is called the hidden layer. You can have multiple hidden layers in a neural network, and ultimately you have finally the output layer, which actually gives you which label it the output belongs to. So one of the main reasons why neural networks actually are capable of drawing these nonlinear boundaries is because every perceptron in the neural network has something called as an activation function, and that activation function is generally nonlinear. So once you actually pass in these inputs, every input is weighted. So there are weighted inputs, and then there's a bias. So you take the sum of the weighted inputs of your features plus bias, pass it to the activation function, and if the activation function exceeds certain threshold, it actually outputs the value after whatever the activation function has determined to the next layer, and the next layer similarly does that. So we did talk a little bit in detail about how these activation functions should be chosen. I talked mainly about three main activation functions. So obviously you can use linear functions, but then we talked about sigmoid, tanh, and ReLU. Nowadays, like ReLU has been very popular because the reason being tanh and sigmoid, though they are nonlinear, but at the ends of their graph, the delta or the rate of change with the error with respect to the weights is really high. The slope changes quite a lot, so therefore it is easily it can easily overshoot, or it does not converge to a proper weight. So that's why we chose ReLU. ReLU is a function which is zeroed for a most amount, and if x is above certain value, it is a constant linear graph, and that's the reason why ReLU has been popular. You can pick and choose which hidden layers use which activation functions. You can pick and choose how many nodes you want in each hidden layers and stuff. So that is pretty much about so the plane linear. This is the activation function. The ReLU activation function I did not mention here, but it is basically equal to x for some value which is greater than some threshold. So basically, if you look at what the ReLU looks like, so ReLU is, if you take f, so f of x, this is your ReLU, is equal to x if x is, let's say, greater than 0, and 0 if x is less than or equal to 0. So the ReLU activation function looks like this. So it's 0 till here, and then after that it is equal to x. So this is your ReLU activation function. So as you can see that until this point it is 0, but after that it has a constant slope. The reason why we need a constant slope is, so we discussed something called as backpropagation the last time. So what backpropagation does is, once you actually take you start off with some random weights, and once you have these random weights, you get some output. And if that output, generally we don't use 1 and 0, we use something like 0.99 and 0.01 as your output labels which you expect. Let's say with these random weights you get some output which is, let's say, 0.7. Then you actually calculate the error. So today when we talk about in gradient descent, we'll deal with how do you optimize this error and stuff like that. But we actually calculate the error between your actual label you got and what, this is your calculated label and what your observed label is. And then this error is back propagated into your network. By back propagation, what we mean is we actually determine, we calculate the error with respect to every weight in your network. If the weight is not if the weight is not directly differentiable, then what we do is we differentiate with partial differentiated with other variables like output 5 and then output 5 with some other x of 5 and x of 5 times this thing. So if this weight lies in like 2 or 3 layers before, so this is the partial differential which you can find out with all the equations, and you will find out what this particular slope is. The way we update the weight is basically, this is called gradient descent. What we do is we take the current weight, this is the new weight, and then we have a learning rate, so we can predetermine what the learning. So there is another code in which you can so we saw one file, we'll do the other 2 programs today. In that we can actually say what your learning rate is. Generally we keep a learning rate of 0.1 or 0.2 times partial differential of this particular weight with respect to the error. So this is how you update the weight. You update the weight and then you again go back and then recalculate your label. So you do that a couple of times, and then you will probably basically stop at some point where your error doesn't change at all. So that is called back propagation. So once more. So we saw what activation functions are. We saw what back propagation is. So the damage function. So we calculate the error, and then once we calculate the error, we actually back propagate it. We saw that with an example also. So let's say if you have these weights, and then these are your input nodes, 0.5, 0.1, and 1 as your bias, and then we did each calculation of what your first net at the first thing is, and then how the sigmoid function would work, and then what the output is. And then you calculate the output again, redo the calculation for these hidden layers the second time, and then you get your final output. And once you get your final output, you calculate the error, which is your target minus output, which is basically 0.01. You are expecting 0.01, but you got 0.75. You calculate the error, and then you calculate the error on both the nodes, and then you do a partial differential of that. And once you get the partial differential of that, you update that particular, if you see this thing here, you update that particular weight by eta times of partial difference. Here we have used the learning rate of 0.5. So this is also one more parameter which you can tune. And similarly, you get new weights. And then once you apply those weights and then recalculate, you will see that the error reduced significantly. So if you do 2 epochs of such training, your error will actually become really less. So we actually used, today we'll be doing one exercise using MNIST database. So go check it out. It has like a lot of images. Basically, it is a database of all images which actually contains labeled data and stuff. And then you can try out different supervised machine learning algorithms to calculate its errors and then find out which is the best machine learning algorithm. So we also saw that using neural networks is an art. The reason being, how many input layers do we use? How many output layers? How many? What is the activation function? What is the training rate? How do you not overfit the data? So these are like the things which you need to answer before you actually create a neural network, right? And you can control the overfitting problem by the number of epochs. But today we will see another network, a more complex network called convolutional neural network, which actually takes care of that overfitting problem, especially for images. So, okay. So is everyone clear with what basic neural networks are? If we are clear with what basic neural networks are, I'll start. Any questions on like what basic neural networks are? Yes, no?
No questions.
Okay. All right. So today we'll talk about a more complicated neural network called CNN. So CNN stands for Convolutional Neural Network. So this is a problem. Why are we, so mostly convolutional neural networks are used for image classification. So if you look at any complex image classification problem, they handle it using convolutional neural networks. So this is one of the deep learning models in which you have like a lot of layers in between. So deep learning is nothing but when you increase the number of hidden layers and you increase the number of neurons per hidden layer, that is called a deep learning network, because you are basically increasing the complexity of your network to such a level that the learning is very deep. It goes and tries to learn the minutest of features of your data set and stuff. But before we learn about convolutional neural network, it is really important to understand what an image is and how do we use so in case of like Indian liver patients, house price markets, and a lot of other things, we actually get so we actually get the features, right? So like for example, let's take the example of the iris data set or the breast cancer data set which we had, in which we have features, or even Indian liver patients, right? So we had 10 features. The features were given to you, so you actually program like maybe like 10 input hidden neurons, sorry, not hidden, 10 input layer neurons, and each feature you hook it up to all these neurons, and then that's how the network will start learning. But if you see an image, let's say if you have an image of a cat or a dog or anything, there are no features here. So what do you think like we should give the neural network? I think I covered this in the last class also. But so how is image processing going to work? Like what are the features which you give for an image?
It's something related to the pixels, right?
Yeah. So I think last class what I mentioned was for an image, if you look at it, like actually, let's take an image. I don't know. Sample images. I have an image. So let me open this image. So I have some image which actually in which I have a particular URL or something. If you look at it, right, like its dimensions, if you look at the properties of that image, so it will tell you like what is the number of kilobytes and stuff. But if you look at the details, it will tell you its dimensions, which is how many pixels is it in the width and how many pixels is it in the height. So every image when you open, so a pixel is the smallest unit in an image, right? So basically when you take an image, you let's say this, I have an image which is 1, 2, 3, 4, 5, 6, 7 times 1, 2, 3, 4, 5. So this is a 7 by 5 image, which is 7 pixels cross 5 pixels. So each pixel, generally if it's a color image, each pixel will have 3 values. It's called R, G, and B, red, green, and blue component. So every pixel, because these are primary colors, so every combination of red, green, and blue pixel values can give you the color. But for simplicity's sake, let's say we take a gray level image, like black and white image. So in that case, it will only have one value because it's grayscale. So it is between 0 to 255. If the value is 255, then it is white. If the value is 0, then it is black. So that's how an image in general is defined. So let's take a grayscale image, which is 7 pixels across 5 pixels, right? So each pixel is basically going to have some property. So in the last class, I actually mentioned that in case of image classification problems, what people generally do is each pixel is fed into, so you create a really high input layer neurons. I mean, you actually have a lot of neurons, and then you have another hidden layer perceptrons. So you give each pixel is passed into different neurons. So this is a fully connected network. So fully connected network means that every pixel is connected to every pixel is connected to every perceptron. So basically you have a pixel 1, so it is connected to 1, 2, 3, 3. You have like a bunch of things, and you have another pixel which is 2. It is also connected to a bunch of these things, and then these are again connected to like a bunch of them. This is like a fully connected like multi-layer perceptron. What happens in multi-layer perceptrons is also when you have these features, you actually pass them to every perceptron in the input layer, and then you pass the output of that to every perceptron in the hidden layer, and then ultimately you have an output layer. So this is again passed to every perceptron in the output layer. So this is called a fully connected network. But just imagine, let's say this is a small image, right? This is like 7 by 5 pixel image. So imagine the number of weights you will have here. So if 7 by 5, that means you have 35 pixels for a small image. So you have 35 input neurons here, and then 35 input neurons are connected to, let's say I create another hidden layer. I create it with, let's say 10. So every 35 is connected to 10. So then it's 10, this is 35 times 35 times 35. So you have a lot of weights you need to train, right? So there are like a gazillion number of weights for, if you combine the weights for this plus this plus this, that's like a lot of weights you need to train using like back propagation and stuff. So in general, your neural network will take ages and ages to train and update. So one epoch itself will take like a lot of time because you're updating it with every weight and stuff. So in general, we generally don't use fully connected layers for image classification. So fully connected layers are not used because it's very difficult to like update weights for every single layer. So then what do we do? So if it is not there, then they came up with something called as convolution. So let's understand how a computer image works. So let's say this is a standard example which most of them take. Let me draw an image which is basically going to be like 2, 3, the same 7 cross 5. Let's say I have an image which is basically, I have to recognize the character X. So the image only has this character X, right? And then my neural network I need to train a neural network. It's a two-class problem. One has the character X and other has the character. Let's say we're playing tic-tac-toe, right? And one person draws X and other person draws 0. Our job is to classify what the person has drawn. So let's say we have other person draws 0. So now if again the same thing, ideally so I'm not saying it is not possible. Ideally you can pass every pixel to train. So you have like bunch of X's, you have bunch of zeros, and you can pass every pixel into your neural network to actually train your neural network and update it, and then determine what that person has drawn, whether he's drawn an X or a 0. But what but then as I said, right, like the update time is really high and it is really difficult to actually train such a network. So people came up with something called as convolutional neural network. Convolutional neural network generally has it has multiple layers. So it has one layer for convolution. I'll tell you what convolution is in a bit. Another layer is called the ReLU or activation function layer. ReLU layer. And then there is another layer called pooling. And after this, they have the fully connected network. Because the output, so let's say if we have a 16 by 16 image, after it passes through the first layer and second layer and third, it becomes a 4 by 4 image. I'll tell you how it becomes 4 by 4. So basically you're compressing this particular image using convolution, the ReLU activation layer, pooling, and it becomes into a 4 by 4 image. So now since this is a smaller image, you can have a fully connected neural network here, which is only having 4 input functions. You will actually pass in every value in here to all of them. So this is easier to train. So what is this convolution layer, right? Convolution layer. So basically what people have recognized is, instead of, so the problem in images is, this is an image in which X is straight, right? So what if so let's say I have 2 images. So first image is X is like this. Second image, my X is slightly tilted. So my X is like this. So it's tilted. So if I pass every pixel into the thing, so it obviously this and this will differ a lot, although they're both the same image. It's the same image of X, but then if you actually take the pixel values of these, right? If you take the pixel values, so this one has a black line in this particular pixel, but since this is tilted, this one will not. So the first pixel is empty. So it is really difficult to train such a model and it will not converge. So what people did is, they actually said, hey, let us do something called as convolution. What convolution does is, instead of calculating the whole X as the image, they actually came up with some parts. So let me actually come up with, convolution is done on a filter. So if you guys have done image processing courses in college or something, you must have learned convolution on a filter. When you apply a filter, smoothing filter to an image, it becomes blurred. When you apply a sharpening filter, it becomes more sharp. High pass filter, low pass filter. Maybe you must have done it in college, or maybe if you didn't take the course also, it's fine. So what this does is, they have like some subsections. So they have like sub images or subsections. So this particular image only learns only learns one section of the image, which is basically, they actually take this particular filter. This is only, let's say, 4 by 4, which only is this thing. And there is another such filter which only learns a smaller cross in 4 by 4. There is another image which learns, sorry. So there's another section which learns the other cross. So if there's a 4 by 4 here, it will learn this pattern. So there's one pattern which is like this, there's another pattern which is like this, there's another pattern which is like this. So what they do is, a convolution is nothing but they overlay these 4 pixels on your image, and then try to see if it matches. They'll give it a value 1. If it doesn't match, they'll give a value 0. So basically it'll try to find only the sublines. The advantage of that is, even though the subline doesn't exist in the first pixel here, but when it comes to the next part, it will still determine the subline, right? Because even if it is tilted, it still has that value of the line there. So convolution is a process where you take a subpixel and then you run it over the image. You run this part, then you run this part, and you run this part, and you run this part. So similarly, you run this part. So all the 4, they run it over all the image. The output of this, whatever the convolution they are doing, is going to be, if there is that particular segment in that image, then that value will be 1. If that segment is not there, generally they take the average of it. So let's say if these two are actually having 1 and 0, or 255, let's say I normalize this. So 1, 0, 0, 1. And this is also 1, 0, 0, 1. They take the average of these 4. So 1 times 1, which is 1, plus 0 times 0, which is 0, plus 1 times 0 times 0, which is 0, plus 1 times 1, which is 1. So if you take the average of that, so if you take the average of that, it is 4 divided by 2 divided by 4, it is 0.5. So it will be the sub output of this, of the multiplication of these 4 with this 4 will result in 0.5, because it's the average of this thing. All right. So is that clear as to? Okay. So average. So they take the convolution of this particular 4 subpixels on every particular 4 pixels of the image. The output of that is, so if you see what is happening here is, these 4 pixels are represented with 1 value, right? It is represented with 0.5 because you're taking the average of it. So now your image becomes smaller because all these 4 pixels are giving you 1 output. The output is put in that particular, the 4 blocks is replaced by 0.5. So that is the convolution. So the idea is, basically, instead of taking the whole X as such, because it will not be invariant to rotations and stuff, you take sub portions of that image. So this sub portion is a filter. You run that filter across all the parts of your image, run this filter across all parts of your image, run this filter across all parts of your image. Let's say if this subsection doesn't exist, then it will become like 0. So the ReLU function actually does that. So remember, I told you what ReLU function is, right? If X is less than certain value, it will be 0. If X is greater than that value, it will be X. So what they do here is, they try to match it with 0.5, right? So if X is greater than, if X is less than 0.5 or 0, it will be 0. So all these filter values will get converted into something like this. So we can actually say, if X is less than, greater than some value, we can give it some value, which is, let's say if it is this thing, then we cap it and say 1. So this image, because we ran a 4 by 4 matrix of this, now this will be smaller. So this will be smaller, and this one, after applying ReLU function, will either have 0 or that image's value, which is 0.5. So this image will kind of become like this, like the X image, because all of them will run, and then each output layer will actually get a value like this. What does the pooling layer do? Pooling, because this is one filter, this is second filter, this is the third filter. Pooling layer combines each of the filters and then gives one image. So this combined image is now lesser in resolution. So instead of, it was 16 by 16 earlier, because we ran 4 by 4 filters on this, now this became a 4 by 4 matrix. And then this 4 by 4 matrix is actually connected to a fully connected layer, and that is the output of, and that is given to a fully connected layer, and the training happens on that. Is this clear? Any questions on how a convolution neural network works? A convolution neural network consists of basically convolution layer, a ReLU layer, a pooling layer. So output of each layer, ReLU layer, convolution layer actually applies filters which are subsections of the entire image. Instead of taking the whole cross, we take one forward slash as one, backward slash as one, mini cross as the other. If you look at the mini cross, it will have maximum value here, but it will not have much values here. So each of them is given an output, and that is passed through ReLU activation function layer, which actually makes values below a certain threshold 0. So it filters out the noise, and then you get basically the output of every filter that is given to the pooling layer. And the pooling layer adds all these things, and finally the output is a much smaller subsection of image, which is then connected to a fully connected network. You can run neural network on this. So most image processing or image recognition algorithms which work use CNNs or convolutional neural networks. Any questions on this?
Can you explain this that grid part where you just compress the
So
image?
let me just do an. So let me just take a simple image. So I'll take the same thing, but I'll just do 16 by 16 instead of taking this thing. So let's get control. Or let me just do 4 by 4. Maybe this will be easier to explain. Let's say I have a cross, right? This is my X, this is my image. So all I'm saying is, instead of, so the reason is, you understood the reason, right? Some X's will be like this, some X's can be tilted. So we need to make a system which is robust. So this is one image which has an X like this. I can draw another image, the same thing. And then this X might be like this. You see, if I try to compare the entire pixel, if I give every pixel to this thing, this pixel has some value here because there's a black line passing through this. This will be like 0. Everything else is 255 because it's white. But in the same time, this pixel is not having the same. So it's the same observation, but this feature actually doesn't work, right? Because this pixel, so this pixel here doesn't have any value, but this pixel has. So it's basically not an optimal way to train an image processing an image by giving every pixel to the neural network. Maybe given enough samples of X, it will probably learn, but it is not optimal. So what convolution layer does is basically convolution. It takes sub portions or sub filters. So instead of matching the whole X, they will run it through 3 filters. So first filter is this in a 4 by 4 matrix, which only has this. It only does this cross. Second filter, what they do is they'll run it with only this. Again, this is 4 by 4. Third filter is, so this is the image in the pixel. The third filter is basically this, which is this slash. So now let's take this pixel, this filter, and run it across this image. So when I say run, it is going to run on this section, and then it will move 1 pixel, it will run on this section. It will again move 1 pixel, run on this section, and then it will run again on this section. So this is called convolution. If you actually look up the definition of convolution, it basically, you take a filter and you run it across all of the image, then it will run across all the 4. It's just like sliding window, right? You slide it like this, you slide it like this, you slide it down. So the reason why it is becoming smaller is because, so let's say we take this filter and then we overlay it with this particular portion. So what is this filter? And when I say run it across, so let's say this filter, for simplicity's sake, I'm saying if there is a black marker present in this pixel, the value is 1, or else the value is 0. This will be 0, this will be 1. Do you agree with this? Like, like ideally the values are 0 and 255, but let's say I've normalized it. And I said if there is a black marker present, the value of this pixel is 1. If it is not present, it is 0. So this one will become 1001, right? In this case, what is the value? This is 1 because there's a black marker present in this pixel. This is 0. This is again 0. This is again 1. Similarly, for this pixel, there is nothing present, so 0. For this pixel, there's something present, so this is 1. So now when I overlay this particular filter on this 4 pixels, I will just calculate to see this pixel times this pixel. So that is 1 and 1. So it is 1. 0 times 0, which is 0. 0 times 0, this is again 0. This is 1 times 1. Like it's just overlaying, I'm overlaying this filter on top of this. And if both of them have black values, it is 1. If they don't, then it is 0. So it is 1 times 1 plus 0 times 0 plus 0 times 0 plus 1 times 1. And I'm replacing these 4 pixels with the average of this output. Average means what? Divided by 4 pixels, right? So this is 2 divided by 4, which is 0.5. So the output of this will be a smaller image because all the 4 have been replaced with 0.5. Similarly, all these 4 will be replaced with another image, which is going to give some other result, maybe 0.25, and maybe this is 0.1, and some of them might be 0. So do you agree that this image is smaller than this image because we are combining 4 of them into 1 point? Does that answer your question, Deepika? Or?
Yeah. This is clear. Thank you very
so
much.
now this becomes 0.5, right? Now the second layer which you pass is basically the ReLU layer. The ReLU function itself says that if x is below certain value, then the f of x is 0. If x is above certain value, then f of x equals x. So let's say if we take this particular value, it need not be 0. Let's say I put this value as 0.3. So now when this function passes through ReLU, x is above 0.5, so this is 0.5. Above 0.45 is above 0.3, so this is 0.5. But this is 0.25. If this is 0.25, we replace this with 0 because if x is below 0.3, then are you guys able to see those ads which are popping up?
No, we are not able to see any of the ads.
Oh, okay. The Chrome is popping some ads. Anyways, so then you pass it through ReLU layer. ReLU layer filters it out. So this becomes 0. This becomes 0.5. This becomes 0. So similar, and so on. So the output after convolution and ReLU is basically going to be a smaller image. But since we run it on all the filters, we have to pool it, right? Because the output, there's an output from this filter. There's an output from this filter. There's an output from this filter. So we actually, then the pooling layer, what it does is it takes all these filters and then pools all of them together. That's a pooling layer function. So the convolution neural network has a convolution layer, it has a ReLU layer, it has a pooling layer. The output of this is a smaller image. Since this image is smaller, then you can actually use a fully connected network on this particular image. And then you can classify your labels and stuff. So this is a very popular neural network in image processing. Is that clear?
Yeah, this is clear. Thank you.
So again, we won't be doing, because there are a lot of things, right? Then how do you choose filters? How do you choose filters? How do you choose like a fully connected layer? So this problem as such is it's only a deep learning problem. You have different nodes, different transformations, different filters. But then after everything is being done, so that's what they use. It's a very popular network used in image processing. That's a convolution neural network. So let's look at another neural network, which is called the recurrent neural network. Basically, before I go into recurrent neural network, so everyone saw what a neural network looks like, right? So you have the inputs. We have first layer perceptrons, which actually the inputs are connected to. Everything has weights, and this is connected to a hidden layer. You can have multiple hidden layers, and then you'll have one output layer, which actually takes the output from each of the hidden layer and then gives you the labels. But then let's say there are some neural networks called skip layer network. So in this, what happens is this particular input actually is given to the next layer also. It skips this layer. The input is given to this layer, and also the input is given to this layer. So there are some networks where, especially in language classification and stuff, where the hidden layer also needs to use that information. Let's say this feature is the language, like which language it is. So even the first layer needs that particular feature, and the second layer also needs it. It takes this particular feature in the first layer, it takes the output of that, and then this input is given directly to the second layer also. So this is called a skip layer network. I mean, these solve different problems, but it is good to know what it is. But another neural network which is really popular is the recurrent neural network. So the recurrent neural network, we'll spend some time on this because most of them, this is a very popular neural network. It's called RNNs. There is another name for this. So RNNs are recurrent neural networks. I'll talk about what recurrent neural networks are in a bit. But how many of you heard of what LSTMs are? LSTM stands for long short-term memory units. So LSTMs are a type of RNNs. So let me just talk about why we need RNNs and what is the use of it. So let's say if you're doing an image classification problem, right? Image classification. So in image classification, let's say you're doing two classes. One class is the dogs, another class is the cats. So now I have first image, the dog image. So the dog image is here. Let's say I have only 4 pixels. It's a 2x2 image. Let's say I use a CNN, or since it's 2x2, I'll just directly use a fully connected network. I have let's say one hidden layer, and then I have one. This is my output layer. So I connect these things. This. Yeah, everything is connected to everything. So let's say I pass this image. This is my training, right? This is my first training observation. So I pass this particular image, and let's say I already trained this thing. This network is already trained. Let's say this is a testing image. This is already trained. This is a test image. So if it is dog, the output will be 1 and 0. If it is cat, the output will be 0 and 1. Right? So I give it a dog image, I got 1 and 0. Good. Now I give it a cat image. The output ideally should be 0 and 1, right? Because we have trained our weight such that when a dog image comes, the label should be 1 and 0. The cat image comes, the label should be 0 and 1. So I have a question. Did the second image have anything to do with the first image? Okay, let me ask this question again. Is the output of the second image, is the output of the first image affecting the output of the second image somehow? So I gave a dog's image. It classified as dog. I gave a cat image. Does the value of, or does the output of the first image affect the second image somehow, like the classification of the second image somehow?
Do they look similar?
No, it's a cat image and dog image. So I'm just asking from a pure, so this is already a trained network, right? When I say it is trained, that means these weights are already fixed. All the back propagation is done. During the training, all these weights are fixed. All these things are now these are all fixed. It's already trained. All I'm doing is testing. In testing, I passed a dog image. So each pixel value, it took something like, let's say pixel value is, mind you have to normalize it. Remember we did standard scalar function last time. So we normalize it. Let's say first pixel value is 0.3, 0.6, 0.8. This pixel value is 0.2. It calculated it, and then it gave the output as 1 and 0. Now for the cat, it has different values, right? Let's say the cat values are 0.1, 0.9, 0.32, 0.55. We give the cat image here. So all I'm asking is, did the input of the dog anyway affect the input of the cat?
No, right? Because it's different.
It is different, right? But the main thing is, ideally, if you were training, it would have affected, because every input is going to change the weights using back propagation, right? If you're training it, if this is part of training in which your weights are still yet to be determined, you'll take the dog output, it won't be close to 1, 0, then you back propagate. You take the cat input, and when you say the output has to be 1 and 0, then you back propagate. But once it is trained, once the network is trained, the output doesn't affect, like whatever you give here, it will calculate its own thing. Like for dog, it will calculate its own output here and output here, and then for cat, it will calculate its own output in each case. So both of them are independent, right? So is that clear why it is independent? Because it's already trained. All you're giving is a different set of inputs. The output of the prior observation has got nothing to do with the output of the current observation. Do you guys agree with that? Is that clear, or does anyone have any confusion?
This is clear.
So, okay. Now let's say you're doing a sentence completion problem, right? Okay, let's say, okay, complete this sentence for me. To be or not to dash. What is this word here? It's a sentence completion. Have you heard of this?
It's B, right?
Is B.
To be or not to be.
To be or not to be. Or like there are some statements like, let's say, lacking. What are some popular quotations? Okay, I don't know. For lack of example, I will say, give me blood and I will give you dash.
Freedom, right?
So it's Subhash Chandra Bose's like dialogue, right? So now I'll ask you this question. Now I'm training a recurrent neural network. I don't know if like I'm sorry, like I studied in India, so for me it is this thing. But I guess Satya, you guys might not have heard of this thing. This is one of the Indian freedom fighters line, so that's why I think Deepika also must have studied in India. So this,
Yeah, that's what I got.
yeah, but the point I'm trying to make here is, you are able to predict what this word is given few words before. Now I ask you this question: is this word output dependent on the previous ones or not? Let's say if I change these words here, will this output change or will it still be the same?
It will change, right?
It will change. So in case of sentence completion or in case of language prediction problems, you see that the previous input actually has a lot of relevance to what your current output is. So this is why there are networks called as recurrent neural networks. Recurrent neural networks, what they do is, they take the output of the previous observation and feed it back into your network, because your previous statement's result or your previous statement's whatever that word is, it is basically used in case. So recurrent neural, again, identify the problem. If it is image classification, you use convolution neural networks. But if you're using any problem on sequential data meaning if the output of your current one depends on your past outputs, then that is sequential. So anything which is in a sequence. For example, prediction of stock prices. Prediction of stock prices, let's say if I take Amazon stock, it was like this and then suddenly it dropped. So if I have to predict this particular value, will you need the values prior or will you not need the values prior? Or is this prediction value dependent on these past ones or not?
It would be, right?
It would be, right? Because you have to know how it is behaving, and then suddenly if it dropped, because it's not independent of what the previous ones are. So all these ones in which the values are dependent on the previous predictions or previous values, they are classified using recurrent neural networks. So in recurrent neural networks, if you look at the diagram, let me show you. So in recurrent neural network, what happens is there is something called as the input layer goes in, and the output of the hidden layer is again passed into the hidden layer. So this is called recurrent neural networks. So recurrent neural network means the same thing is recurrent. But the idea behind that is some information which it learned from the past is useful in predicting the next information. So in such cases, in ordinary case, it's simple feed forward network. You have input layer, hidden layer, output layer. But then in case of like language sentence completion problems, like if you look at it, like most of these even like emails these days, right? Like if you're typing something, they'll predict what you're going to type. So let's say if I type like I say have a nice, it'll say day. It'll automatically try to predict what it is. That's because it has learned so many documents that it knows that whenever have a nice comes, the automatic prediction is a day. So the way those things are learned is using recurrent neural networks. Recurrent neural networks, the output of a previous layer is again passed along with the input. So this is at time t, right? So this output is at time t. So this time is t, but then next observation comes at time t plus 1. So this input is given along with the time t plus 1. Let's say this we call this c of t, and let's say I call this input. So in I of t is passed, and you get c of t, which is the information with the past output. Now the c of t is passed along with the next sequential item, which is I of t plus 1, and ct is passed along with it, because this ct will help in the prediction of this problem. So that is what recurrent neural networks do. So recurrent neural networks are mainly used. It's also another deep learning algorithm, but they are mainly used when you should identify. That's why the class of the problem is important. You should identify when they'll be useful. They are mainly useful in cases where the output of the previous information, like in case of language sentence completions or stock price predictions and stuff. So there are different kinds of neural networks. So there is a very popular neural network. This, if you take like deep learning classes or something, I mean, or this is like advanced level of machine learning. It's called LSTM. So LSTM stands for long-term short memory. So what it does is basically it's a more complicated model than this, but it tries to remember what happened in the recent past. So long-term short, it has a short memory, but it retains that short memory for a long time. So let's say if it'll like stock prediction, they use recurrent neural networks quite a bit. So what they try to do is if they remember that recently the stock price has dropped, they'll remember that, oh, it has dropped. So they won't predict a price which is ridiculously high, because it has to follow certain trend. So they keep a short-term memory of it, and then it goes further. But if you look at the different ways in which recurrent neural networks are there. So there's a time delayed network. So in which they take the output of something, delay it with n seconds, and then give it here. So then that is called a time delayed recurrent neural network. In this case, like maybe the third word is more helpful in prediction of your current word than the previous word, in which case they delay it by certain time and then give it back to the same network. So there are like different combinations of recurrent neural networks over time you will see. So that is basically, so these two are really popular, CNNs and RNNs. So you will hear the terms if you're actually doing machine learning, and if you're doing neural networks, these two are like really famous neural networks: recurrent neural networks and convolution neural networks. Is that clear? Any questions on recurrent? So we won't be, again, as I said, we won't be touching into the complex nature of these things, but yeah. but but I just wanted to explain what these networks are. So we will look at them later on. Questions on recurrent neural networks? No questions? All right. If there are no questions, then let's look at like some pros and cons of neural networks. So neural networks, first and foremost, they're very flexible. They can approximate any like nonlinear equations and stuff like that. They are extremely powerful if you add more and more layers, because more layers will actually increase the complexity of learning. But some of the cons are basically the training time is going to be huge. Large computational powers are required for performance, and it is very difficult to know what each layer is learning. So you can't generally. So that's why people just do deep learning and then they just play around with and then look at the ultimate results. They don't know what individual layer learns or how it actually how it propagates its learning to next layers and stuff, how the back propagation happens and things like that. So it is basically not easy to theoretically understand what it is doing, but at the same time, but if you have enough computational power and stuff, it is basically useful to learn these networks and stuff. So one of the things which we saw in fully connected, so how do you actually uh, program for like recurrent neural networks or like highly convoluted neural networks and stuff? So any deep learning neural networks, basically there is any deep learning neural networks, there is a library in Python called Keras. I want to talk about this library a bit. So Keras is exclusively for deep learning. So Keras is basically, it is fast, it is efficient. So you can actually use the MLP classifier. So on like last class we saw MLP classifier, right, in sklearn library. So there one library which we learned was sklearn. So that had MLP classifier. So MLP classifier actually is a fully connected neural network, and it will learn different classes and stuff. But anything which has like lots and lots of training hidden layers, lot of input neuron, lot of neurons per layer, we use deep learning. So deep learning, and this has to be built fast, and it should be easier to code. So Keras is the library which Python actually uses, but Keras is only the front end. Keras in the background, it uses TensorFlow. TensorFlow is this library from Google. So actually you can install TensorFlow also. So you can, so if you just go type TensorFlow, you can install that package. So I have a whole presentation on TensorFlow. Maybe we'll do that next time. So TensorFlow is basically this. So TensorFlow is basically a Google product. It was originally developed by Google Brain team. So Google Brain actually does some cool stuff too. Like it does like, how many of you saw what Google Duplex? Have you heard what Google Duplex does? How many of you heard about Google Duplex?
Yeah, I've heard of it.
So Google Duplex is this team. What they try to do is they try to simulate human voice through a robot. Like it learns how humans pause. Sometimes we say it even learns those things. So it's a very complex neural network written by their team actually did that project, but TensorFlow is something which Google actually sponsors, which is basically it is for faster execution of deep learning. So imagine the number of computations that go on, right, in case of deep learning. So there are like thousands of nodes, thousands of weights need to be updated, thousands of each back propagation epoch itself has like thousands of computations in which the weights need to be updated, right? So they actually created a new language called TensorFlow. It's actually in which they say that every function is a tensor. So I have a small exercise which I'll probably do next class, where I don't want to teach you another language, but we can see the basics of how TensorFlow works. I'll show you, I'll execute it and then show you that. But in brief, they have something called as TensorFlow. So where they define that every tensor can be viewed as a multiple array of numbers. So everything in this particular box is a tensor. So tensor, a scalar is a tensor, a vector is a tensor, everything is a tensor. That's why it's called TensorFlow. And then the way they give the tensor inputs is by actually giving two tensors and say matrix multiply. This is like really fast. And then addition, and then they do apply a ReLU function. And so maybe when I do the example on TensorFlow, you will probably understand how. So there's a construction phase and execution phase. But TensorFlow is a software in itself. The main use of TensorFlow is you need to learn how to create tensors. So you need to take the data and then convert it into this tensor model. So it's a data structure in itself. And then once you create tensors and you call the tensor functions, it does your mathematical calculations really fast. Like how many of you heard of CUDA? CUDA is basically this NVIDIA's parallel processing code. So if you're doing parallel processing, so CUDA actually is a language in which you can you know, right? Like if you actually install a GPU on your system, you can leverage a lot of calculations to GPU, which will happen really fast. So a lot of people install GPUs on the system when you're doing TensorFlow algorithms and stuff like that, because GPU actually has the computational ability to parallelly execute a lot of executions within like a second. So instead of it can run around like 30,000 or 300,000 operations in 1 second simultaneously. All you need to know is if you learn the CUDA language, you can take a particular process and then you can, using CUDA, you can parallelly make it into small bits and give all of them in one time and then combine them together. So anything which takes like 30 seconds, if you learn CUDA and then do it properly, it will take 1 second, because all these sub things will run in 1 second. So 30 operations can be split into 1 second operations of 30, and then you'll get the output in 1 second. So it's used for really fast learning. Similar to CUDA, there is TensorFlow is basically a particular way in which you categorize your data into tensors, and then you do tensor operations on them, like matrix multiplications, additions, and stuff like that. So it would basically work on like huge data sets, and it will basically learn also much. Remember, I was telling that OkGo, or the Go game, which Google had created, that was on TensorFlow. So you can actually see that TensorFlow has like the highest. So other thing is Theano, PyTorch, and all these things are also other parallel listing. But then TensorFlow actually, so Microsoft also has something similar. It's called CNTK. So cognitive, I think it stands for Cognitive Neural Net. This is toolkit, and Cognitive Cognitive Network Toolkit. So basically, it also runs in parallel this thing, but Google has done like some more work on this thing. So basically, they have something called as TPUs. And you have GPUs, you have CPUs, and then they're called TPUs. You can see like a image of how the TPUs are stacked up in like the Google Cloud and stuff. So they'll execute these things really fast. So instead of you installing TensorFlow and then doing all that, so the Keras library does that for you. So you need not learn this new language now. So all you need to do is basically install Keras, and then once you install Keras, you basically so. Are you guys able to see my screen? The whiteboard?
Yeah, we're able to see.
Yeah.
So the Keras library actually takes this TensorFlow software or TensorFlow units, and then it wraps this behind the scenes. So in Python, you will actually just load the library called Keras. And I need to, as I said, right? So so if you're actually having a TensorFlow already installed, you'll have a conflict because Keras also tries to install something. So just for this class, I'll do a small exercise for you in TensorFlow, maybe the next class, and then we will see how that runs using tensors and stuff. But in Keras, if you are having TensorFlow, please uninstall it and then install Keras for one of your programs right now. So Keras actually runs TensorFlow in the background. It has its own libraries, but for you, you need not like worry about splitting the data into tensors. You need not worry about all that stuff. So you just install Keras and then you'll run your code and it'll run it for you. But there are certain things in Keras I need to tell. There are something called as sequential models and functional models. So sequential models in Keras, and then there is something called as non-sequential models. So non-sequential models and sequential models. These are two models in Keras. So sequential model is basically the model we use for general fully connected layers. So you actually have these things. So they operate in a sequence. So you have like first sequence, second sequence, third sequence. So these are connected to each other, and these are connected to each other. And the output is based. So you have inputs, and then you have, you have inputs and you have outputs for each layer. So this is a sequential layer. And mostly in this class, we will use only sequential model. But if you want to use something like RNNs, right, where it's not sequence but output of one is actually input here, or if you want to use that skip layer network where it is not in one sequence but the sequence is disturbed by giving input of some other past events to the current hidden layer, or you want to skip the input to one of the, or if you want to skip like one of the features, if you want to skip one hidden layer and give it here. So they fall under non-sequential layers or functional unit. It's called functional models. So this is a little, again, as I said, this is probably a next level class. It's not, won't come under an introduction to machine learning, but I'm just telling you this so that in case in the future, if you do end up like coding with like non-sequential models, you will basically you'll end like RNNs and stuff like that. You'll actually have to use non-sequential data. So this is about Keras. So Keras basically has two models. It actually runs TensorFlow at the background. It has like a lot of other things for normalizations. Just as we had like in sklearn, we had like standard scalar, which actually normalizes things, right? So Keras has its own thing. So you use Keras only when you're doing deep learning. Don't use it, or else it's just an overkill. Like you create tensors and stuff, something if it doesn't need that many computations, and it'll only be useful for neural networks. So I don't think Keras, maybe they have it, but I don't think it has other machine learning algorithms like Purple vector machine learning. Anyway, so since we learned a little bit about Keras, so last class we saw how we used MLP classifier. So let me go to the code now. So before I start gradient descent today, I want to like do a little bit on all right. So let's see. So last time's code, if you look at it, so I think we did press cancel. Right. So yeah, we used an MLP classifier with hidden layers. So this is basically a standard sklearn library. So this sklearn library actually also you can create a neural network using MLP classifier. You can actually split the data, train the data, and then you can create a hidden layers with this. So this is a simple network. But if you look at the next thing, which is digits, not digits. So in MNIST, you can see that there are other functions to it too. You create the hidden layers. You can tell what is the maximum number of iterations you need. You can specify the learning rate and other functions to it as well. So MLP classifier, so sklearn is pretty good for like the ones which we are doing. But there is one example, I think digits also use sklearn. They're different I just wanted to show different data sets which use MLP classifier. But I think if you look at this function called, I don't know if I sent you this. If not, I'll send you this now. So it's basically using ANN on Indian labor patients. So this one actually uses Kira's model. So Kira's models, I use sequential model. Dense means fully connected. So if I say dense, so basically I create, can everyone see my screen? You can see the code, right?
Yeah.
Okay.
Yeah.
Cool. So basically in Keras, I just, so the same like fully connected output neuron or the neural network output is, I can model it in Keras as well. By calling Keras models, I use the sequential. We use sequential and dense because we are doing a fully connected neural network. And then it's actually write this. It's like just few lines, not even like 3-4 lines. So it's very simple. First install Keras library, create a new project. Or no need to create another project. If you have like artificial neural networks, just go install Keras library, import Keras library.models, import the sequential model from it, and import a dense model. So here you import the Indian liver patients data, which is basically the cleanse data which you got from your class 2 or 3. And then you basically do the this thing, like you create, you take the first 10 columns, that is your feature vector. The last column is your label. So you create a model which is sequential, and then you keep on adding dense layers. So this is like 12 is your input. 12 is your input layer, and then you have 8, which is your hidden layer, and you have 1, which is your output layer. Because it's a one-class classification problem, right? So you basically it'll either be class 1 or 2. So and then you can change the activation functions which you want to use for each of the models too. And then you compile the model, and then you fit it, and then you run it. So basically you can see that. So ideally this actually oh, I actually just installed TensorFlow, so it messed up with the Keras. So don't worry about this. I will. It worked last time. It is not working now because I just installed TensorFlow to show you guys this thing. So as I said, right, Keras has its own implementation of TensorFlow. So you'll run into this issue if you first install TensorFlow or first install Keras. But in general, like this ran last time. I pretty well remember this thing. So it's not running now because I must have messed up my TensorFlow module. So I'll fix it, but then you guys, if you actually just install Keras, it will install TensorFlow in the background, and then you can actually change your dense layers. You can do. I mean, right now we are not teaching non-sequential models, but if you want to do like RNNs or you want to do some skip layer networks and stuff, you'll use the functional layers. And even active, the transfer learning. I said you can train one model, you can connect the input layers of that model to your current model, and then that is called transfer learning. The weights of that model will actually be learned by someone else, and you're just transferring their learning into your network. So if you want to do such things, you have to use non-sequential models in Keras. So I think that pretty much completes our lecture on neural networks as such. Are there any questions? So everyone understands like activation functions, backpropagations, like deep learning, recurrent neural networks, convolution neural networks, Keras models, sequential model, dense models, non-sequential models, sklearn, MLP classifier and stuff. Any questions on this?
Will we be coding this? No.
I would have wanted you to code, but Maheen is not running because
Okay.
I installed Tensor. But you can code it. Like Actually, because you guys never, how many of you use TensorFlow? If you have used TensorFlow, maybe you'll run into this.
No, I have not used it.
So if you don't have TensorFlow, it should work fine for you.
Okay.
So if you actually, so it's just few lines of code. So I think you can do it at home also, but I'll send this code immediately after the class. So it's basically, the concept is pretty clear. You just take your data set. Here I'm not even splitting it into test and train because I'm, so okay, tell me one thing. How is this calculating its accuracy if you're not splitting it into test and train? Here there is something called as model fit. You actually give the batch size here. This is doing the k-fold validation. Some of you, I don't know if you have attended the lecture on k-fold validation. So if not, just go through k-fold validation lecture. I think some of you must have missed that. So we have discussed, like, in k-fold validation, you basically, so in general, right, in most of the cases, we do test train split. If people, like, if you've been coding along with the class, this is like a very common thing which we do. We do this thing where we split the data into 70% and 30%, and then test train split. But in this case, we are doing a batch, like the k-fold validation of in the batches of 10. So we keep 10 of them aside, and then we train on the other whatever is there, and then we evaluate this, and then we again evaluate the next 10, things like that. So it's a very simple algorithm. So you create the sequential model, add your dense layers, and then compile that model, and then evaluate it on Excel. So there is one thing actually I want to talk about today. I think gradient. So if you are worrying about this loss function, I'll talk about that in this class right now. So the next part of the lecture, I want to talk about optimization functions. What are cost functions? How do you what are loss functions? What are loss and cost functions almost mean the same. And then how do you optimize that? What are the different techniques used for optimization stuff? And then we have, I think I sent the houseprices.csv to everyone today. So today we'll talk about three optimization algorithms. One is called gradient descent. Other is least mean square, and other is called stochastic gradient descent. So these two are optimization functions. Before I start gradient descent, I actually mentioned gradient descent somewhere else in my lecture too. Where did I mention it? You guys have been following. So we've already used gradient descent somewhere. Can anyone tell me where have we used
it? Regression?
We didn't do regression, right?
Oh, sorry.
You did it, but I didn't do it. That logistic regression and linear regression we will learn when we teach R. So that will be the last two topics we learn before we end the class. But you're right, it is used in anywhere you want to optimize something, you use gradient descent. But in our lectures, we've learned, so there are two means to actually optimize something. I've actually mentioned gradient descent 2 times also when I was teaching that.
CNN, right?
Where are we actually? What are we optimizing in CNN? We're not optimizing anything.
That back propagation.
Yes,
no.
Back propagation is where. So I've been telling you that we're updating the weights, right? So basically this equation which I was telling you, when weights are updated. So basically, remember we actually had an error, and then I said this error is back propagated, and then we update the weights. The new weight is basically old weight minus some learning rate times partial differential of that weight by W old. Is this equation familiar? This is what we do in back propagation. In back propagation, we optimize the weight. by actually taking the partial differential of the error with respect to the weight, and then we change the weight by certain delta, and the way we determine that delta is basically this is nothing but gradient descent. This whole process is called gradient descent. I've actually mentioned when I was doing backpropagation that I'll teach this when we do gradient descent. Ring any bells, or have you guys forgotten how we update the weights or something? This equation is familiar, right? Like this is how we update the weights, and then we update the weight in every epoch and then go back and then get the new error. Again, update the weight, again go back, get the new error. So we do this iteration in every epoch. You guys remember it now, or?
Yeah, I can remember.
So this is how we actually update the weight in every iteration. So this process is called gradient descent. So, but before we do gradient descent, there are some terminologies we need to learn. So first and foremost, cost function or loss function. This is this terminology is used quite a bit in machine learning. So what is a cost function and what is a loss function? So they're interchangeable. So whenever we have something which we need to optimize, right? Like for example, in the case of neural networks, we had to optimize the label output, right? So we had computed label, computed minus expected whole squared. We did half of that. So this is our error term. So by optimization, I mean that this has to be as close as possible to 0. So these three things mean the same: cost, error, or loss. Loss function, error function, or cost function, all three mean the same. So all we need to do is whenever we have the cost functions on this thing, we have to, so there's a significance of this thing. So there are a lot of times we optimize for maximization, but we never try to maximize the cost, because anything which is costly, we try to bargain and get it down, right? We never go and say, I'll pay you more. The cost function, losses also, we want it close to 0. Error, we want it close to 0. Cost, we want it close to 0. So that's why cost function, error function, or loss function all the three mean the same, and we want them to be as close as possible to 0. So that means that this is an optimization problem. In this case, this is the error. I want to optimize, or I want to make it as close. So what is the minimum value this can take? Just look at this equation and tell me what is the minimum value this can take.
0.
0. Let me ask a maths question actually. So I have a square plus b square plus c square equal to 0. What are the values of a, b, and c?
0, right?
Why are they 0? I mean, obviously, if they're all zeros, we will get the answer. But why do you think they're zeros?
Because
I mean, it's non-negative. All of them are non-negative.
So a square is always positive, b square is always positive, c square is always positive or equal to 0. So if 3 positive numbers add and if the result is 0, there's nothing to negate the positivity from something else, right? So if 3 positive numbers, when you add and it comes to 0, that means all 3 have to be 0. It can't be anything else, because if you have 2, you'd have some minus 2 somewhere to make it 0, right? But if you're only adding positive numbers, it's always going to be positive. So positive plus positive plus positive equal to 0 will always be, all the 3 have to be equal to 0. So anyway, so in this case, all these loss functions, if they are to get a minimum value that is equal to 0. Now, how do we actually compute these error functions and stuff like that? Is basically one such method is called gradient descent. So gradient descent is basically it's an optimization technique in which you optimize. So it is used in a lot of places. When we do linear regression and logistic regression also, we will see how gradient descent is used. So gradient descent is one such technique using which you can find the minimal value of a function. So it's an optimization technique. So let us actually look at some basic math. Let's actually look at some basic math functions. How many of you know what a convex function is? Have you heard of convex functions before? So basically convex function actually is a, sorry, was someone saying something? Anyway, so convex function is a function, if I actually have to describe, if you take 2 points within that function and you draw a line, if all the points lie within the same function, it's called a convex function. For example, this function, you see the red line is a function, and I take 2 points within that function boundary and I draw a line. All these points are within that boundary, as long as the endpoints are within the boundary. If I take 2 endpoints and then endpoints are within the boundary, if I draw a line, it basically means that all the points will be within that boundary. So this is a concave function. A concave function means, or non-convex, I shouldn't say concave, but a non-convex function means that if you take 2 points within the boundary and then I draw a line, you see this segment of the image is outside the boundary, this segment is outside the boundary. So this is not a convex function, this is a convex function. Now, why are we learning convex functions and concave functions? I'll tell you in a bit. So if a function is convex, then if you actually, so this is like, again, basic algebra in high school. So when you want to find a function, if you want to find its minimum, you actually take the partial differential of that function with respect to the variable and equate it to 0. And that's how you will actually find out what the optimal equation is. And if you take the double differential of that particular function, if it is negative, then it is minimum. If it is greater than 0, it's maximum. These are like, I won't go into like details why these are, but I think you must have learned it in high school as to why double differential of something less than 0 is basically minimum, why greater than 0 is basically maximum. So if a function is twice differentiable and the second derivative is non-negative, then the function is called convex function. If the second derivative is positive, then it is called strictly convex function. If the function depends on several variables, a function is convex. Anyway, this is like a math, this thing. I'll actually show you why we'll use this. The main reason why we are learning convex functions is because we are trying to find the optimization, right? We are trying to find the minimum of a particular function. So if a function is convex, then if there exists some minima, then it will always be the global minima of that function. So I think it spends some time to understand what I'm saying here. So if a function is convex, let's say this is a convex function. If at all it has a double differential, right? If you try to take the differentiation and equate it to 0, find the values of x, you'll always find that there is one particular value for which it is minimum. But that minimum is always going to be the global minimum. Now, what is a global minimum? What is a local minimum? If you take this function, you'll understand. Look at this function. This is sine x by x. So it's like this. So if I try to equate the equation of this to 0, I'll get a lot of points for x. This was 1 point because equation is nothing but the slope, right? The differential is 0. That there's one slope here, 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 one slope here. So you will find a lot of minimums for this. That is because these are local minimums, because it's not a, whereas if a function is convex, as soon as you differentiate it, it will always have only one minimum for a convex function. But if the function is not convex, it will basically have like a lot of functions. So that's why we learn about convex functions, because when we are trying to optimize an equation, we need to know whether it's convex or non-convex, because then we will know if we are finding the local minimum or a global minimum. Is anyone having any confusion about what local minimum and global minimum is? Or why we have to learn like convex functions and like, why do we care about local minimum and global minimum?
Because that gives you the cost, right? The least cost.
Yes. So basically, when we are trying to actually optimize the cost, we always want to minimize the cost which is least. Let's say if I have a function which is like this. Can anyone see what I'm drawing? I don't know if you can see that. But let's say if I have a function which is like this. Now, let's say this is our error function, right? And now if this is supposed to be minimum, I have to find a value for which error is minimum, which is here. But if it is like this, every time I differentiate, if I find this value, this value, this value, I won't know which is my minimum function. So I'll train a network such that my error has to be minimum, right? I'll train a network which will find its local minimum, and then it will still have a lot of error because it's a local minimum. It is not a global minimum. So you always try to optimize the equation such that we find a global minimum, not a local minimum. So that's why we need to learn about convex and then concave functions. And then there are some properties of this thing. So there's something called as Lipschutz function. Lipschutz function, if the first derivative of the function is bounded in some interval, then the first so this Lipschutz function tells you whether a function has first derivative, whether it has close. So these are like mathematical concepts behind it. But then ultimately what we care is if gradient descent can be applied to a function or not. If the gradient descent does not, if it cannot be applicable, then you will get like random results. Then you will know that it is not one of these Lipschutz function or non-convex functions. So we'll do the other way around. We'll just apply the algorithm for everything. If it doesn't converge, the reason is it. Ideally, we need to know this because if you are actually a true data scientist, you have to like look at the data, figure out the equation to see whether it's convex, non-convex, and then see whether gradient descent is the best approach to optimize this particular algorithm or not. So as I said, right, like weights, the weight equation needs to be derivable, and it needs to actually uh, uh, that's why we use some standard functions. We can't use every function. We use like sigmoid activation functions for neural networks. We actually use only some standard functions. If it is not derivable or anything, then we won't have an optimal weight to train the network. So that's why we first have to look at those functions, look at them and see before we actually choose them as activation functions. We need to look at them and see if they make sense or not. So having said that, we actually use optimization techniques in a lot of cases. We use them in, so these two topics we'll cover in the end, linear regression, logistic regression. The reason is ideally everyone starts the course with this, but we'll do it in the end because the case studies we have for this are in R, and we haven't studied R yet. So that's why we'll do this later on. But uh, it anywhere, like anywhere where we want to fit a certain model or we want to find an optimal weight. Actually, someone who is dropping in. Is someone having internet issues? Oh, okay. Anyway, so basically, in logistic regression and stuff, everything boils down to if you want to find the best equation, we want to find the. So anyway, I'll just tell you what we can look at the math later on. So basically, linear regression means it is a model where you predict how the data behaves. So remember, I said regression means prediction and classification. So I talked about like major machine learning classification problems. So most of the classes we have seen so far are on classification. we still didn't touch regression. Regression means predicting. So when you have a set of points like this, let me just show it. So when you have a set of points which are, so regression means you have to predict something. When you have a set of points which are like this, right? So x, this is y and this is x, and then x and y are like this. So these are your training data. You have to predict the value of y such that for given a new test data x, you need to predict what the value of y is. So in linear regression, what we do is we try to fit a linear model. So we try to fit one line through this model such that this line can actually represent this particular data. So I think we did a couple of examples in the past to say that, hey, you know, if I have to like predict unknown value of this, the best fit for this is, let's say if it is linear. So linear regression is exactly that. Linear regression means how do you fit a model such that this data is best represented. Now, how do I use gradient descent here? The gradient descent is used for optimizing error, right? So I can fit one line like this, I can fit another line like this, I can fit another line like this, I can fit another line like this. But if you actually take the residual score, residual means like after you fit it and you take the distances of these points to the line and you sum them up, those are the errors, right? Because this line is this much away from the actual predicted value. So this is error 1, this is error 2, this is error 3. So we sum all the errors together. So, and this is for this line, but for another line there is some other error, right? For this line you have to draw the perpendicular distance from this point. You see that this error is larger. So for all the lines, when you calculate the errors, you have to find that equation such that this error is minimum. This error tends to go to 0 or whatever it is. So that's why we use gradient descent in linear regression. So the idea is to make this cost function. The cost is nothing but the summation of error squared. This has to go to minimum, or not 0 but minimum. So we need to find such a line such that this cost function actually becomes minimum. So that's why whenever you have the function like this, you use gradient descent to find out what is the value of x which will give you this error minimum. If you look at it, even that's what we are doing even in neural networks. We are trying to find that particular value of weights such that the error is minimum. So is it clear, like where are we using, like why do we need to learn gradient descent and where are we using it and stuff? Okay. So we will actually, so there are other optimization techniques also. We'll see QR decompositions and stuff like that. We can actually, in matrix theory, there are like a lot of other decomposition metrics. But the thing which we are going to learn today is gradient descent. So a very nice example of gradient descent is this thing. So what are we trying to do? So let us take Mount Rainier or any mountain any mountain which you like maybe Everest or that. So what are we trying to find in this thing? Let's say if this is your error function. So we are trying to find a point. Let's say if the mountain is inverted, right? So if the mountain is inverted, the point which we are trying to find is basically the global minimum, or this point here. How do we determine that point? It's like, let's say if you drop a ball somewhere here, which is and it has some velocity, which is the point where it comes and settles down? That is basically the bottommost point in your mountain, right? So the approach for this is relatively simple. Let's say you're somewhere over here, or let me ask this question to you guys. Let's say you're somewhere over here. Imagine that anti-gravity or something, and you have to reach this point. How will you know when you reach that point?
When you start going back up.
Okay, that's one way of doing it. Like you keep going and then you actually keep going down, and then suddenly when you feel like you're going up, That's when you will feel the
Isn't isn't the minimum and the maximum and the velocity zero?
Sorry, repeat that question.
The minimum and maximum is like when the velocity is zero. So like when you're basically a point where you're almost stopping, that's when the minimum is.
Well, you're taking the ball example, but let's say you are on that mountain, right? And let's say I blindfold you. You are blindfolded on that mountain. You have to reach the minimum point in that mountain. The reason I'm asking this question is the answer to this is exactly what gradient descent does. So let's say I blindfold you and I leave you on a mountain which actually has slopes somewhere. Like I leave you somewhere here on this mountain, and you're blindfolded. And I tell you, like, go to the most minimum point. How will you go?
So we go to a place when the slope is zero.
Yes, but you're blindfolded, right? So what will you do? Because you're blindfolded, you won't know where the slope is and everything, right? You won't calculate that, right? So, okay, let me give you the answer, right? So basically, the thing is, you basically will take one step in every direction around you. If you feel that yeah, I mean, you're right, but you just take a step, and if you feel that the slope is increasing, you won't go in that direction. You will basically go in that direction where you feel that the slope is decreasing. Ultimately, when you actually reach the most minimum point, in all the directions you go, the slope will be increasing. There won't be even one direction where you feel that the slope is still decreasing. So that is pretty much what gradient descent does. So if you take this mountain as your error function, and this step as like the direction in which you take a step as one of the variables, it will try to change that variable delta, a small variable delta, such that the error is becoming minimum. If the error is not becoming minimum, then it won't go in that, it won't change that variable anymore. The problem with this is, like, let's say this mountain is like pretty clear. We have one global minimum. But look at this mountain. It has like so many minimums, right? So if I leave you somewhere here, you can settle here, you can settle here, you can settle here. Depending on where you are, you might get settled. So that's why you have to be little careful with convex functions. So, sorry, you have to be careful with non-convex function. In a convex function, the local minimum is your global minimum. But in case of non-convex functions, you won't have in case of non-convex functions, it won't be the same. You might end up at some local minimum and think that is basically your this. So the concept behind gradient descent is, if you take the mountain as your error function and the directions as each of your parameters, you try to change the value such that you try to change every parameter by delta W such that you basically have the slope in the negative manner. So that's exactly what so it's pretty much the same thing what I told you. So there is one thing, it's called the learning rate. The learning rate is basically nothing but the step size. If you take a small step, you'll learn slower. If you take a bigger step, you'll learn faster. The problem with if you have a really high learning rate is you might take a really big step and you might miss the minimum somewhere. So the learning rate has to be optimal such that, but if it's really small, you might take forever to reach that minimum. So it has to be somewhere in between. You can't completely have a really big learning step. You cannot completely have a small learning step such that you won't be there. But that's pretty much what gradient descent does. What it does is, so gradient descent is widely used in data science. A gradient measures, so the term gradient means the slope. So gradient, if you actually look up the English dictionary, it also means the slope. It means how much delta of like one variable depends on the other. So what is slope in case of like in case of algebra, you take delta y by delta x, right? So if I have an equation of a line, the slope of the line is basically y2 minus y1 by x2 minus x1, which is delta y by delta x. So a gradient measures how much the output function changes if you change the input values by little. The advantages of gradient descent is very simple. It's computationally fast per iteration, low memory requirements. That's why it's become really popular in case of data science. So let's look at how it is basically done. So the thing which it says is, it's exactly how you update your weights So gradient descent is a first order iterative optimization function to find the minimum of a function. To find the local minimum using the gradient descent, one takes steps proportional to the negative of the gradient, because you want to go to the point where your slope is minimum, right? So that's why so if you look at it, your weight also is updated such that, so the reason you say, old weight, some learning rate times the slope. So if your slope is negative, then you update your weight, which is positive. If your slope is positive, then you decrease your weight. So that's why that's the whole equation of gradient descent. So what he says is, you actually change your x such that it is proportional to some alpha times of the gradient of that particular function. So if the alpha is small, then it might take forever to get to that place. But if the alpha is large, we might miss the thing. So alpha should probably be somewhere in between so that we don't miss that particular point. So if f is convex, all the local minimums are also global minimums. The gradient descent can set we have converged to a solution. But if it is having local minimum, so it still doesn't solve the problem of how do you avoid local minimums, right? Because even though like you reach a point, let's say you reach a point in your mountain where it is a local minimum, if you take a small step in every direction, you will still feel that that is your global minimum, because take a small step in every direction, the slope increases. So you'll think that you will lie there. So how do you actually handle that? That is basically, it's basically called stochastic gradient descent, in which I will talk about that later. So in this case, what you do is, so there is, so now let's talk about the cost function. Least mean square is basically the sum of all error terms, least mean square. So basically, if you have an error, this is the same equation we'll use in linear regression also. But it means that if you have a predicted error, so in case where you predict some particular output value, you take that minus your input value, that is your error term, half of that. So even in case of, you saw that in case of like neural networks also, we did the same thing. We took the error term, and then what we did is we update the value of the weights. In this case, we update the value of whatever is your input parameter, which is x. You're trying to fit ax plus b, right? So you try to update a and b such that for the same x, that error is minimum. So the way you do it is you change this a by saying a old. The new a will be a old plus some delta a. This delta a should be proportional such that you go in the negative direction of the slope. So basically, it is equal to negative times of the error with respect to your a. So that's how basically your gradient descent algorithm works. You first take you take the squared of the error, you sum the error, and then you differentiate that with respect to the variable you're trying to optimize. And then when you actually equate that to 0 and solve for the equation, you will get your optimal values. In case of linear regression, we'll get the optimal a, and so if you have like ax plus b, if this is what you're trying to predict, you will get optimal a and b. In case of like neural networks, we get optimal weights. So note that like W0 and W1 are updated for calculation over m samples. So we actually take it over different samples and then we do it. So there is some process called as stochastic gradient descent. Stochastic gradient descent is nothing but here we try to go in every direction, right? In case of so we try to differentiate every unknown value, like W1, W2, W3, or the way you look at stochastic gradient descent is, let's take the mountain example only. So the mountain example, what he says is, instead of trying out in every direction, we just try out on some directions. So the reason for that is, since the updates to W are done for all the observations into account, the gradient descent is very slow for large data sets. For example, let's say we have like 1 million observations. So that means that we need to do 2 million sums of these W's to optimize for that value. So 2 million operations is really large, right? So another way approach is to update the weights of each sample. So we update the weight instead of running it over all observations. We will run it. We'll update it for each sample. After every sample, we'll update it. This is called a stochastic gradient descent. Due to its stochastic nature, the pattern is zigzag. So what this means is, like in that mountain example, you were going in all the directions to find where to go, right? So in this case, you're saying just do a zigzag method. Like somehow go this way, this way, this way, this way. You'll ultimately land here if your number of observations is really large. So in this case, what we do is after every observation, we keep updating the weights. For one or two, so the general steps are for one or more epochs or until the minimum cost is reached, we will update the weight for each sample. And then we will see, hey, after going in this zigzag manner, I went this manner. Is this minimum? No. I go again in this manner. Is this minimum? No. This manner. So we actually go zigzag till we actually reach the global. So this is stochastic gradient descent. So there is a compromise between, it's called mini batch gradient descent. It's a compromise between stochastic gradient descent and gradient descent. In this case, for some samples, we'll update it for all the observations. For some other samples, we will basically update it for some variation. So we generally won't use this minimum mini batch gradient method. We'll generally use stochastic gradient or generally gradient descent approach. So how do we do this? So if you want to use stochastic gradient descent in sklearn, there is a package called as stochastic gradient descent classifier, SGD classifier. So in sklearn, there's a linear model stochastic gradient. So we actually will do an exercise on this. So the main thing what it takes is, it takes the loss function. What kind of error is your loss function? What is your learning rate, and what is the number of iterations through which I need to optimize? So ideally, you can keep on iterating through like a lot of epochs, right? So it will directly ask you what, like how many iterations should I go to find the minimum this thing. So that is basically pretty much our lecture on gradient descent and stochastic gradient descent. But let us do some exercises on that. So I'll just show you. So the house price or CSV, I sent to you guys. So here there is, in this case, we are trying to predict, basically there's a square footage of the house and there's a price of the house. So in this case, I'm trying to find out. So using gradient descent. So this particular program, what I did is, I didn't use any library. I tried to implement exactly what I said. So I'm trying to fit like a model A and B such that I can actually guess this data correctly. So you have the square footage and you have Y, right? So if you look at the data here, the data is basically you have the square footage and the price. So you basically have X and you have Y. So I'm trying to predict a line which actually can explain this data the most. Why am I doing that? Because if I give an unknown square footage, you'll actually look at that point on the line and say, which is the best price you can estimate for it. But among all the lines, I want to find out the line which actually has the least error. So the way I did it is basically I calculate, let me just do this. Firstly, I calculate the value of Y. I have to predict what A and B are such that I come up with a model where Y equals AX plus B. So one function I wrote is get Y, which is A. Okay, this is BX plus A. So I think instead of writing A equals B, I wrote BX plus A. But so I actually return the value. And then what I do is get least mean square. So what does that mean? I have a predicted value, right? You have a predicted value, which is Y. And sorry, you have an actual value, which is basically coming from your square footage. You have a predicted value, which you get by putting AX plus B, and then you return the sum of it. So that is the least, that is the error term. And then what you do is you take the delta of A and delta of B. So how do you do that? It's basically when you take the value, so you're trying to do this function, right? So you're trying to find out delta error with respect to A and delta error with respect to. So let's say if your predicted Y, this is predicted is with AX plus B, So what is your error function? Y hat minus y, right? So it is whole squared. So it is ax plus b whole square minus y, whatever is your prediction. So this is your error function. Oops. This is your error function. So you take this thing with respect to a. So you try to differentiate this with respect to a, you will get 2 times of ax plus b minus y, and then multiply it with 2a. So this will be your dou e by dou a. So I'm just trying to update my new a such that it is old a minus some learning rate times dou e by dou a. I'm just trying to hard code whatever this step I've done here. I've just hard coded that. Look at this. So that's what I did. So I basically tried to find out what dou e by dou a is, and then the same thing with b. And then for every plot, I tried to find out what that particular value is, and I started with some random values. Initially, that's the same thing with even in case of weights, right? We start with some random values, and then I stop the model when the error rate becomes less than some epsilon. The epsilon which I have is basically a really small value, and then I iterated. So I iterated like 100 times, and let me plot this. So this is just for your knowledge. So you can directly use the gradient descent classifier from sklearn, but I hard coded it just to explain, the I hard coded it such that I explain what the predicted values is. So this is basically giving you the predicted values for different. Sorry, this is the actual values. Now I'll try to fit a line through these things. So this is your square footage and your cost. So I'll try to optimize it for 100 iterations. We will see. Initially we drew a line which is like this. I got high error. Then I changed a. Then it will become like this. Become like this. It will become like this. And if you see here, it is converging to one value. After it comes to this particular point, it won't change much further, because at this point is where your error is mostly zero. So it will kind of converge to this value. That's how you'll determine what the best fit of the line. Is that clear? Any questions on this? Are you guys following this, or?
Can you show the coding, like
Yeah.
the logic again?
So the logic is, this is kind of like, all I'm trying to do is, okay, so the problem is basically, so this is the best line which fit this. So this is exactly your linear regression also. Like that's what we do in linear regression too. So the thing which we are doing here is we have the house prices, right? So we have a certain X, we have a certain Y. We have such things. So we are trying to find out what is the line which fits these points the best. So we have certain points. So we have some points. This is your training data, which is the house. This is the square footage, and this is the cost. So we have these points, which is basically your training data. Now I am saying, for me to, so this is actually an introduction to linear regression. This is what linear regression does. In order to, like, now I gave this points. Now if you give me some new point, how will I figure out what is its cost, right? So in order to do that, I need to come up with an estimate of how this data behaves, right? So I'm saying that I'll try to estimate this data by saying a times x plus b is my new. So I need to find out a and b, because a and b are the parameters here, right? X and y are already given to you. I need to find out a and b such that I can, so ax plus b is a line, right? So I try to, if I actually plot this line, it should have the minimum error. Now, what is the error here? Error is nothing but your predicted value, which, let's say if this is my line, right? So if I say, okay, if the cost is this much, what is my predicted value? My predicted value is this, y hat. But what is the original value? Which it is this. So we try to basically take that difference. So we take error is nothing but for all the points, 1 belongs to n, we take this difference. For all the points, we take y hat minus y whole squared. So this is my error function. So this is my error. Now what I'm doing is I'm trying to change. So if I have to change, if I have to come up with, I initially come up with some random a and b. I say a is 30, b is 1.2, random. Then I calculate what the error is. Now the error is really large. That means my a and b are not optimal. So now what should I do? I should change my a. I should change a to a prime, which is my new a. But how do I do that? That is where I'm using gradient descent. Gradient descent, what did we find? A prime is equal to a minus delta a. And this is what we saw through gradient descent. It says like a minus some learning rate times differential of error with respect to a. So now this equation, you can just plug it in, right? So a hat is what? Ax plus b minus y. This is yi. So if I take the partial derivative with respect to a, then this will become like 2 times some, like 2 times ax plus b minus y times x. So I plug this thing back into this equation. So all I'm doing in this code is just that. I'm trying to iterate this like n number of times. So let us look at the coding. So again, you need not write this by yourself. You can directly call the library. So if there is a library called USCast, standard scalar, and then the library is called stochastic gradient descent regressor. It's for a linear model. So you can call the library and that will do that for you if you specify what kind of loss function you want to optimize. So I did it like the hard way because just to explain the concept of what I'm doing. So in this, let's look at the code with this particular. So first I wrote a function which is ax plus b. Then I wrote another function which will give me the error, which is nothing but half of y minus y whole squared, right? So it is basically half of that. Then I did delta a. Delta a is given by basically the negative, so NP sum of this over all points. If you saw my error equation, if I take the partial derivative of with respect to a, then that will come out to be as y minus y hat negative times. And then if I take with respect to b, it is this times x. This is nothing but the partial derivative of with respect to a. So over all the points, what I'm doing is, if you calculate this over all the points, I'm calculating my new, so I'm calculating my new x and y with, and then I'm using this learning rate. I'm using an alpha of 0.01, and epsilon is basically the difference. So we cannot exactly get zero error, but if my error is some 10 to the power of minus 8, I'll stop. So if you look at this thing, while this minus this, while my old minus the old least square minus the new error least square is greater than this thing, I keep on iterating it. How do I iterate it? I calculate what delta a is and I calculate what delta b is from the above equation, and then I update my a and b. A is equal to a minus alpha times delta a. B equals b minus alpha times delta b. So I update it using gradient descent, and then I calculate my new error. So if this new error, while this new error minus old error is still greater than epsilon, I keep on iterating this. But I also plot for every 100 iterations, I plot that graph. The number of iterations, mod 100 if it is 0, then I'll print out that iteration number, and then I will calculate what that plot is, and I'm plotting that. So if you see here, So this is the original data. So you see that, this is the thing. So for 100, 200, 300, 400, 500, 600, 700. So after 12 iteration, after like 12,800 and 12,087 iterations, the error is like less than 10 power minus 8. So this epsilon, so the old minus new is less than 10 power minus 8. Then I stop here. So this is just to show you the number of, so this is plotted every 100 iterations. So I do 100 iterations, I plot this. I do 100 iterations, I plot this. Ultimately, you see that after 12,800, after 12,087 iterations, this thing converges. So then you will say that this, once, whichever one it converges to, you will say that, hey, this is the line which fits this data the best. Any questions? Deepika, is that clear, or have any questions?
Yes, I, this is clear. Thank you.
So all I'm doing is using gradient descent to find out the best line which fits this. In fact, this is something we will even see in linear regression. So linear regression means that how do you find out a linear relationship between x and y points? How about others? Do you guys have any questions on this? Satya, Meher, Satvik.
No, makes sense.
Yeah, I'm good too.
What? You mentioned the coupon?
So that's what gradient descent actually does. So instead of doing this manually, you can actually use something called as a stochastic gradient descent regression. It's part of sklearn's linear model library. So what you do is you basically take some feature data sets. You do a scalar transform of it because you want to actually have both x and y in the same format. So you want them to be normalized between 0 and 1. Then you fit a model based on squared laws. That's exactly what we did in gradient descent. Fit the model and you say predict, and then you actually take the error. So you calculate the total error in this case. So if you run this, you will actually see that the linear model for this So every time it fits the model, it will keep on reducing the. So this is y and y predicted, but we also calculate the. I didn't print out the error, but if you actually see the root mean squared error for this thing, it will keep on reducing for every iteration of this. So you see the total root mean square error on this is 4 point something. And these are the values which you get with what you have predicted. So this is so you actually have test. On the test, you actually fit your model. And on the train you fit your model. And then on the test, you predict what the values are. So you will see how, so if it is 24, we have predicted 30. If it's 21, we predicted. So it will show you the error for the best fit, which we have. So there are two ways you can use stochastic gradient. Either you can code it yourself by taking what that A and alpha delta A should be, or you can use a standard library called stochastic gradient descent regressor. So in this, what we did is basically we did the scalar transform, which is normalize the data, and then we created a model which is again it's on the same lines as how we did other algorithms. We actually got a stochastic gradient descent regressor, and we fit a model for squared laws, and then we fit that and we predicted it on the test samples. So then I printed out what the total error is, and then I have the regression method in which I actually printed out what the root mean square error is, and then the difference between y actual and y predicted values. Actual values is this is what we predicted. That is the best fit which we've got so far. Any questions on this? So now you understand why we need to learn gradient descent, because gradient descent is how we determine what the optimal parameters are when we try to fit. It need not be optimal parameters. Like in case of artificial neural networks, it helps us to determine what the optimal weights are to train a network as well. So when we are training a network, it basically tries to fit or find out what the optimal weights are based on a cost function. The cost function or error function is nothing but the difference between the predicted value and the actual value. So we want to minimize that particular value. Questions? So I'll send both the code for this and the neural networks code for Keras. Please try to run the Keras yourself. Need not to, you can run this just to see how gradient descent works, just for your understanding. But try to run gradient descent on something. So do this. This is basically I'm using some other data set, right? Try to get the same. Try to predict. So given the house price data, try using the stochastic gradient descent regressor instead of calculating it manually. Use this on the house price and find out the line which best fits it. So here we are actually loading some Boston data to do it. Instead of doing that, load up the house price data and try to fit the best model using the stochastic gradient descent regressor. Questions?
No questions.
Okay. I think that's pretty much what I had for today. Next class I'll show you how to run TensorFlow. Because you'll be done with the Keras assignment today, right? So afterwards, even if you install TensorFlow, it shouldn't matter. So, but then after that, if you just want this to remove TensorFlow, so we'll do TensorFlow the next class, and so we will do this thing. So TensorFlow, and then we will do random forest. So we'll do three concepts: bagging, boosting, and random forest next class. So again, I wanted to let you know. So not this Sunday, but next Sunday we won't have a class. We will use that to basically finish your assignments and go through all the algorithms which we learn the next Sunday. Because after that Sunday, so I'll finish bagging, boosting, and random forest the next class, and after that we'll do one more algorithm called naive Bayes algorithm. So after naive Bayes algorithm, we will stop with all the classification algorithms and supervised machine learning. Then we will go ahead and do regression problems. Before that, after the next Sunday, we'll have like two more classes. So one class we will basically do R, and the last class we will do logistic regression and linear regression test case study in R. So that way you will get like you'll learn R and you'll finish like the case studies. So any questions so far on like what we've learned today, or what else is left in the course, or what we are.
No questions.
Is anything like, is everything clear, or is there any, if there's any concept or anything which is bothering you, please ask. So if there are no more questions, then I'll send this codes to both the files and gradient descent. Lecture. Are you guys thinking about it, or like, is there anything which you want? I can go through any of the other features.
I'll actually go through whatever you have done and then see if I have something, and I'll let you know by next
So
class.
then next class, let's start like 15 minutes.
Okay, yeah. Thanks.
All right. Thanks everyone. We'll meet again on Sunday.
Thank you.
Thanks, Sai. Bye-bye.
Bye.